Okay, in this video, we're going to be talking about problem number 22, 6.22. All right, let's start with part A. For part A, we want to show this identity here. So let me take the right-hand side of the identity and then write it in the following way. 1 over 1 minus x times 1 minus x to the n plus 1. This is equal to, we're going to use the result that we have from a previous problem. I think it's problem 6.20, but I'm not sure. You can check for yourself if you're interested. But I can write this 1 over 1 minus x thing as 1 plus x squared plus all the way up to infinity. All right, that's an infinite sum. Times 1 minus x to the power of n plus 1. Now, this is very simple because what you can do is you can FOIL, okay? You can take the 1, multiply everything by the infinite summation, and take the x to the n plus 1, multiply everything by the, I'm just foiling here, okay? There's nothing fancy going on here. So let's FOIL. We have 1 plus x squared plus dot dot dot, all right? That's just 1 times everything here, minus x to the power of n plus 1 plus x to the power of n plus 2 plus x to the power of n plus 3 plus dot dot dot. All right. Now, if you stare at this long and hard, you'll see that that this is just equal to 1 plus x squared plus all the way up to x to the power of n, because all the things that come after x to the power of n, they're gone. Why? Because they got subtracted. Okay, thanks to this term. Okay, if this term does not exist, we wouldn't have been able to subtract off all the terms that come after x to the power of n. Okay, so that was part A. For part B, part A was very straightforward. Let's go ahead and take a look at part B. For part B, we want to have an expression for the partition function. Okay, the partition function is just a sum over Boltzmann factors. Okay, what's a Boltzmann factor? Well, a Boltzmann factor is negative energy of some particular state over tau. We're summing over all the states. Now, what are the states that we're summing over in this case? Well, in this case, we're just talking about the rotational states, right? The z component of the magnetic dipole moment is quantized, okay? Is quantized. Therefore, there is a number, j, which could be equal to 1/2 or 3/2 or 1 or whatever, and this number determines the quantization. Okay, there's the energy levels are quantized, and if you look at the prompt, you're going to see that the z component of the magnetic dipole moment, that is just negative j times the number delta mu, or negative j plus 1 delta mu, or dot 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 dot, or all the way up to j delta mu. In other words, if you measure the z component of the magnetic dipole moment of the particle, you'll see that it could not be continuous. It has to take on discrete values, and these are the discrete values. Of course, with each of these values of the z component of the dipole moment, there is an energy associated with it, because this dipole moment interacts with the external B field, if there is one, of course, which there is in this case. So so what we are going to do is we're going to write the energy of each state as negative mu dot b, which is just negative mu z times b, because b is in the z direction. This result, if you don't know where it comes from, it comes straight out of E&M. Okay, that's just like introductory E&M. There's nothing fancy here. So let's write everything that we talked about into this partition function. So we have a sum over some number n. Okay, this number n could range from negative j all the way up to positive j. We have this summation here of Boltzmann factors, negative beta is just 1 over tau is just kt if you don't know, times energy of the state, which is negative mu zb. All right, now this is equal to a sum over n of e to the beta mu zb. Now, what is mu z? What is it? If you look at the prompt, you'll see that mu z, you don't even need to look at the prompt, I already wrote it here. Mu z could take on these discrete values, and these values are determined by two numbers, j and delta mu. So we have the summation of n from negative j to j of Boltzmann factors of e to the power of beta times b times n delta mu. All right, that's just mu z. That's what it is. So what is this equal to? Well, we want to define a new variable, b equal beta delta mu b. All right. We are defining it. You don't have to define it, but defining it this way make things a little bit less messy. So this is equal to, if you use the new definition of b, you can write the summation as sum over n of e to the power of, let's see where our b is. We have beta here, delta mu here, and b here. So that's little b, okay? The three things come together, they form little b. So we have e to the power of nb. Now, let's define a new variable called x. X is e to the power of b. Now, the reason I'm doing it is because I can write this as a sum over n of x to the power of n. Now, what is this equal to? This is just x to the power of negative j plus x to the power of negative j plus 1 plus dot 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 plus x to the power of j. All right. Now, what is this? This is just x to the power of negative j times 1 plus x plus all the way up to x to the power of 2j. All right. Now, I'm going to use a result that we obtained from part A, and then if you define this thing as m, we just have x to the power of negative j times 1 plus x plus dot 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 plus x to the power of m. What is it? If you use the result from part A, you'll see that this is equal to x to the power of negative j times 1 minus x to the power of m plus 1 over 1 minus x. Okay, that just comes straight out of part A. That's the whole point of doing part A, is because it's so that we can use it here. So now we need to do a little bit of manipulation here. Okay, we're going to manipulate this. We're going to massage it. This expression, I can write it as this. Okay, because that's what it is. All I did was I took the x to the power of negative j and wrote it on the denominator because I can. Now, now you can write this as 1 minus e to the power of b, 2j plus 1 over e to the power of bj, 1 minus x. Okay, because x is equal to, and I remind you, x is equal to x e to the power of b, and m is 2j. Okay, so if you substitute everything in here, you're going to get what I get here. All right, that's just algebra. There's nothing complicated going on here. So, but that's not the goal. The goal is to show that this is equal to the expression that we're given in part B, which is a fraction of sinh something over sinh something. We want to show that this is equal to sinh b of j plus 1/2 over sinh of b over 2. So how do I show that these two things are equal? Well, very simple. I'm going to use the definition of the hyperbolic sign and write this as e to the power of bj plus 1/2 minus e to the power of negative b j plus 1/2. There is a over 2 here, and let's see, for the denominator we're going to do the same thing. For the denominator, we have b over 2 minus e to the power of negative b over 2 over 2. Okay, the 1 over 2 cancel. Now what I'm going to do is I am going to multiply both the numerator and the denominator by this number, e to the b over 2. So now I just get e to the power of b j plus 1 minus e to the power of negative bj over e to the power of bj, excuse me, e to the power of b minus 1. So now I am going to do another thing, which is multiply top and bottom by e to the bj. Okay, if I do that, I'm just going to get e to the power of b 2j plus 1 minus 1 over e to the power of bj plus 1. Excuse me, that's not what I wanted to write. I can write this denominator as e to the power of bj times eb minus 1. Now I can write this as 1 minus e to the power of b 2j plus 1. I am multiplying top by negative 1. That means I'm going to have to multiply the bottom by negative 1 as well. So if you do that, you have e to the bj 1 minus eb. Now, if you look at what we got before, if you look at this, and you compare it to this, what do you see? You see the same thing, right? You see the same thing because there's an x here, which is e to the power of b, okay? You see the same thing, that means they're equal. That means we're done for part B. So we have successfully derived an expression for part B for the partition function, and then we showed that this expression in terms of Boltzmann factors and stuff is in fact equivalent to the expression that we're given, which is a fraction of sinh something over sinh something. They're equal. They're equivalent because of the definition of the hyperbolic sine function. Anyway, that was a lot of algebra. Let's go ahead and move on to part C. We want to show that the total magnetization of a system of n particles is equal to this long expression, which I'm not going to bother writing down. But let me remind you of something. The total magnetization of a system of n non-interacting particles is equal to n times the magnetization of one particle, the thermal average, of course, of the magnetization of one particle. Okay? So if you want this, you need to first get this. But this is very equal to get. Very easy to get. Why? Because a thermal average is just a sum of the variable that we're looking for times the probability of that particular state, right? That's just standard expression for the average value of some observable. We all know this from quantum mechanics or whatever. So what is the variable that we're looking for? Well, the variable that we're looking for is in fact the z component of the dipole moment, the magnetic dipole moment. That's what we call the magnetization. That's what magnetization means. It's the z component of the magnetic moment. It doesn't have to always be the z component. Sometimes if you're just talking about the magnetization in a general context, then we're just talking about the magnetic moment. But in this case, since the B field is in the z direction, we're only interested in the z component of the magnetic moment. That's why we're talking about mu z here. Anyway, the probability, what is the probability? Well, the probability of each of these states that we're summing over is just the Boltzmann factor over the partition function. All right. Now, what's the Boltzmann factor? Well, the Boltzmann factor is E, energy of the state over tau. This is, of course, a function of state. It is not a constant. Now, what is the energy of these states, right? What is it? Well, it is in fact e to the power of negative. The energy of each state is just negative. Let me remind you that we have obtained an expression for the energy of these states from part A or something, but we have it. It is negative mu zb, okay, over tau. Mu zb just comes from mu dot b, but b is in a z component, so you just have mu zb. Now this is equal to mu z over z times e to the beta mu zb. All right. Now I'm going to write this as 1 over z times mu z e to the beta mu zb. All right. We're of course summing over all the states. Now, if you look at this expression that we got, what is it? There's a very cute way that you can write this expression, because this is just equal to mu z, you can pull out a factor of mu z from the exponent if you just differentiate this exponential. All right, you can do it. Before I pull the derivative trick, let me first rewrite the mu z as n delta mu. That's what mu z is, where n is the variable that we're summing over, which can range from negative j to positive j. So that's mu z. I'm going to write the same mu z on the exponent here. So we have beta b n delta mu. Now, because delta mu is a constant, I'm going to pull it out of the summation. So we have delta mu over z times a sum of n, n e. Let me remind you of beta, b, and delta mu. This combination of three variables, they make up a new variable called b that we have defined before. So we have nb here. Now I am going to pull the derivative trick, okay? Because how do you pull a factor of n out of the exponential? You differentiate the exponential with respect to b. That's how you get a factor of n in front. All right, that's very cute. That's very, very, very cute. So we just have n, a sum over n of derivative with respect to b of the modified version of the Boltzmann factor, I guess you can call it that, nb. Okay, if you don't believe me, just go ahead and differentiate. If you differentiate this exponential with respect to b, you're going to get a factor of n in front. Now, a sum over derivatives is a derivative over sums. So, in other words, I just want to pull the derivative outside of the summation. Because I can, because that's calculus 1. Now, the reason I did that is because if you look at this, what is it? Just ask yourself, what is this thing? What is it? Isn't it just a partition function? That's just a partition function. Okay? This is just a partition function. You substitute all the weird variables back in, like b. If you substitute b back in, b is beta, b delta mu. You're going to see that this is just a partition function. It really is. So now you see a very interesting pattern, because we have 1 over z times the derivative of z. What does that remind you of? It should remind you of the natural log function. Okay? It should, because this is just the derivative of the natural log of z. Okay? If you don't believe me, you just do the derivative yourself. So now, the reason this is good, the reason I'm bothering doing this is because we have an expression for z, and it's a very convenient expression too. And we derived this expression from part B, so I'm going to pull it out of part B. Part B says that z is sinh of b of j plus 1/2 over sinh of b over 2. Okay? It just comes straight out of part B. So now this thing I'm going to write as log of sinh of bj plus 1/2 minus log of sinh of b over 2. All right, because the natural log of a fraction, you can write it as a natural log of this minus natural log of that. Okay, that's the property of natural log. Now I'm gonna differentiate this thing first, and then differentiate that thing, and then subtract them. Okay, because I can. That's because the derivative of a plus b is derivative of a plus derivative of b. That's calculus 1. So now we have 1 over sinh of b of j plus 1/2 cosh of b of j plus 1/2 multiplied by j plus 1/2, because chain rule, minus 1 over sinh of b over 2 cosh b over 2 times 1 over 2, because chain rule. Okay, now this is just equal to these two things together. They form a cotangent, a hyperbolic cotangent of b of j plus 1/2 times, of course, j plus 1/2 minus hyperbolic cotangent of b over 2 times 1 over 2. Now, if you look at the expression that we have obtained, it is exactly the same expression as the one given in part C, except for the extra factor of n in front. In other words, there's supposed to be a factor of n here. Well, our expression doesn't have it because we're just calculating one particle here. This is the thermal average mu z for one particle. Okay. If there's n of them, you just multiply this thing by n, and you'll get the total value. So m, where there's n particles, is equal to n times average m for one particle, where average m for one particle is just this expression, which is the same thing as the one that we're supposed to be getting. So this is all for part C. Let's go ahead and move on to part D. Let me put a QED here just for completeness. You want to show that the magnetization has the expected behavior as t goes to 0. Well, as t goes to 0, remember, b goes to infinity, because b, as we defined it, is proportional to beta. What is beta? Beta is just 1 over t times a factor of Boltzmann constant, but that's not important. So in other words, we really want to take the limit of the expression that we obtained from part C. We are going to take the limit of that thing as b goes to infinity. Now, if you look at it, we have a hyperbolic cotangent here. We have two of them. So we are interested in the limit as x goes to 0, as x goes to infinity, of hyperbolic cotangent. So this is what we're interested in. What is this? Well, this is the limit as x goes to infinity of e to the x plus e to the negative x over e to the x minus e to the negative x. That's just the definition of the hyperbolic cotangent, okay? Now, if you substitute infinity here, you get 0. And if you substitute infinity for x here, you get 0 again, so you just have 1. All right, you just have 1. In other words, let me use a different color here. At high values of b, this thing is 1, and this thing is also 1. You have 2 of these 1s here, 2 of them. So I can write the m as delta mu, n delta mu, of course, because there's n of them, times 1 times j plus 1 over 2 minus 1 times 1 over 2. This is n delta mu times j plus 1/2 minus 1/2. The 1/2s cancel. We have n delta mu j. All right. So what does this mean? This means that as the temperature goes to very low values, the magnetization of the system of n particles starts to approach this value of that is determined by the value j. In other words, all the particles, you know how they have a dipole moment, right? And this dipole moment could point any directions, but as the temperature goes to very, very low values, all of the particles, they point along the direction of the B field, because you remember the B field points up, it points in the Z direction. So this thing here is just saying that for low temperatures, all of the particles, they align themselves with the B field. And if you don't know why that is, you should think about it. Okay? But that's all this is saying. And that makes sense that for low temperatures, all of the particles align themselves with the B field, because that's the lowest energy configuration. It is. Because you remember the energy of the coupling between the B field and the magnetic dipole moment is can be expressed as negative mu dot B. Okay, so in other words, this is negative mu Z times B. So this is a positive number, and this is a positive number, of course. So the larger this number is, the lower the energy is. All right, that is why the lowest energy configuration is for all of the particles to align themselves along the direction of the B field. Okay. Now, I have a little picture that I want to show you that graphs this expression for m as a function of b. Now, if you look at this, let me zoom in on this. The horizontal axis is b. Okay, so as you can see here, for high values of b, in other words, for low values of temperature, the m, it starts to approach j. Okay, it starts to approach j. When j is 1, m approaches 1. J is 1.5. M approaches 1.5. Right? It approaches whatever j is. And if you look at the expression that I inputted in Desmos for m, you notice that I divided out the constant factors of n and delta mu. That's why m approaches j. Otherwise, m is going to approach n delta mu j. But n delta mu is not important, so I divided it out. So this is an interesting plot for you to look at. But at the end of the day, this is the expected behavior as we have derived here. So that was part D. Let's go ahead and take a look at part E. Oh no, my terrible handwriting. For part E, we want to show that for high temperatures, the magnetization is proportional to 1 over T. In other words, we want to derive Curie's law. How do we derive it? Well, first of all, we want to derive we want to derive an expression for hyperbolic cotangent when the argument is very small. Okay, so let's do that first. So hyperbolic cotangent of x is equal to e to the x plus e to the negative x over e to the x minus e to the negative x. Okay, we want to look at this as x goes to 0. Okay, so what is this? Well, I'm gonna Taylor expand this. I'm gonna Taylor expand these exponentials. All right. What is an exponential? Well, exponential is 1 plus x plus 1/2 x squared plus 1 over 6x cubed plus higher order terms, right? I'm going to ignore the higher order terms because the value of x is really, really small. So in other words, I'm going to substitute this expression in here. So we're looking at x limit as x goes to 0 of 1 plus x plus 1/2 x squared plus 1 over 6x cubed plus all the higher order terms, which I'm ignoring because I can, because x is very small, plus 1 minus x plus 1/2 x squared minus 1 over 6x cubed plus higher order terms, which I'm ignoring for the same reason as before. So on the denominator, we have 1 plus x plus 1/2 x squared plus 1 over 6x cubed minus 1 minus x plus 1/2 x squared minus 1 over 6x cubed. Now, let's expand this thing out. Plus x minus x, they cancel. Minus 1 over 6 plus 1 over 6x cubed, they cancel. So we just have 2 plus x squared on top, and plus 1 minus 1, they cancel. Minus 1/2 plus 1/2 x squared, they cancel. And let's see, we have 2x plus 1 over 6x cubed. Not 1 over 6x cubed, 1 over 3x cubed, because there's 2 of these 1 over 6's. 2 times 1 over 6 is 1 over 3. Now, if you look at this, I'm gonna divide top and bottom by x because I can. Okay, limit as x goes to 0 of 2 over x plus x over 2 plus 1 over 6 x squared. Okay, now I'm gonna divide both top and bottom by 2. We have limit as x goes to 0 of 1 over x plus x over 2 over 1 plus 1 over 12 x squared. Now, I realize I made a little mistake here. This is not 1 over 6. This is 1 over 3, because 2 times 1 over 6 is 1 over 3. So we have a 1 over 3 here, and this is not 1 over 12. This is in fact 1 over 6, because 1 over 3 divided by 2 is 1 over 6. Again, I'm not doing anything fancy here. All of this is just algebra. I am dividing this by that, adding this to that, and all that sort of thing. You are more than welcome to go through this algebra yourself, if that makes you feel more comfortable. Now, what I'm going to do is something rather fancy, but not really, because I'm going to write this as 1 minus 1 over 6x squared, because there's a reason for it. And the reason I can write this thing on the denominator as this is because 1 plus x to the power of n is just 1 plus nx, basically, for small n. Of course, there's higher order corrections, but I'm ignoring all the higher order corrections because as long as x is small, then this expression is reasonably accurate. So what do we have on the denominator here? On the denominator, we have 1 plus 1 over 6 x squared inverse. Okay? Now, this is really just 1 plus negative, because negative is what n is. N is negative 1, 1 over 6 x squared. That's why I pulled this denominator up, okay? I basically just shifted denominator up. And I can because of this wonderful little formula here, which derives from Taylor expansion. All I'm doing here is I'm taking limits and doing Taylor expansions and algebra. Okay, this is a very cumbersome calculation. The whole thing, the whole part E, is a very cumbersome calculation. There's a lot of these little steps, but at the end of it, at the end of the day, this is just Taylor expansion. I'm just Taylor expanding everything, and algebra, of course. But anyhow, I can FOIL this thing, okay? And that's what I'm going to do. I'm going to FOIL it. I have 1 over x minus 1 over 6 x plus x over 2 minus 1 over 12 x cubed. X cubed I am going to ignore. It drops out. Why? Because it's very small. Remember, we're taking the limit as x goes to 0 here, okay? When x goes to 0, a very small number, if you multiply itself, if you raise it to the power of 3, it's going to be even smaller. Okay, so it drops out. We can ignore it safely without consequences. Now, what is this? Look at this. What is it? This is plus negative 1 over 6 plus 3 over 6 times x, right? What is it? This is 1 over x plus 1 over 3x, right? This is hyperbolic cotangent in the limit as the argument goes to 0. So we have derived an expression for hyperbolic cotangent in the limit of small argument, and we're going to use this in the expression for m. Remember, m is n delta mu times j plus 1/2 times a hyperbolic cotangent of b of j plus 1/2 minus 1/2 hyperbolic cotangent of b over 2. But remember that what we're doing here is we're taking the limit as b goes to 0, because we're talking about t going to infinity. That means b has to go to 0. So in the limit of 0, b, we have n delta mu j plus 1 over 2 times 1 over b times j plus 1 over 2 plus b j plus 1 over 2 over 3. All right. There's a bracket here. Minus 1/2 1 over b over 2 plus b over 2 over 3. Okay, now the algebra begins. The algebra begins right here. J plus 1/2, j plus 1/2, they cancel. And this becomes a squared. Okay, so we have n delta mu 1 over b plus b over 3 j plus 1/2 squared. Okay, minus this cancel, and this becomes this thing becomes a squared. Minus 1 over b minus b over 12, I believe. Now 1 over b cancel. We have n delta mu. My handwriting is so horrible. N delta mu b times some number c, okay, minus b times some number d. All right, I'm not going to bother writing down the number. You know, it's just a number. J plus 1/2 squared over 3. That's just a number, so I'm going to write it as a constant c. N delta mu times b times whatever number that is. Okay. Now this, as you can see, this is proportional. This whole thing is proportional to b, right? Because we have b times n delta mu times whatever number it is, times whatever number these two things are. But the point is that m goes like the first power of b. It goes like b. But what does b go like? Remember the definition of b. The definition of b says that b goes like beta times whatever, times some number. Okay? But what does beta go like? It goes like 1 over temperature. Because beta is defined as 1 over kT. So the point is, the moral of the story here is that for small values of b, the total magnetization goes like 1 over t. You have an inverse power law here, inverse t to the power of 1. That's Curie's law, and that's pretty significant. It's pretty interesting and pretty significant how we can derive Curie's law just from basic ideas like Boltzmann constant and you know, there's nothing fancy or complicated going on with this whole problem. And we were able to derive we were able to derive Curie's law. Anyway, that was just a curious observation. Let's go and move on to part F, which is the last part. The last part, let me pull out my notes here. Let me remind you of the formula that we derived before for a two-state magnet. Okay, this is the formula that we derived before. N delta mu over 2, hyperbolic tangent of b over 2. All right, this is the formula from before. And we want to show that our result that we got from part C reduces to this result when j is 1/2. So all we got to do is to plug in the 1/2 to m and see what we got. So we have n delta mu. Well, j plus 1/2 is just 1, so I'm not going to write it anymore. Hyperbolic cotangent of b minus 1/2 hyperbolic cotangent of b over 2. Now we're going to do some manipulations here. And let me take a look at what the manipulations are going to be. Oh yeah. So what we're going to do here is this. We have n delta mu times 2 over 2 times hyperbolic cotangent of 2 times b over 2 minus 1/2 hyperbolic cotangent of b over 2. All right. Notice I'm not doing anything here. I'm not doing anything that is out of the ordinary here, because 2 over 2 is just 1. 2 over 2 is just 1. I am not modifying the original expression. I'm just rewriting it in a different way. I am multiplying everything by 1, because I can. This is equal to n delta mu. What is this? What is this? I have to remind you of something that you might or might not remember from your previous math classes, and that is that we have properties for hyperbolic cotangent. And some of you might remember, some of you might not, but I can write this as hyperbolic cotangent of b over 2 plus hyperbolic tangent of b over 2 minus hyperbolic cotangent of b over 2. For those of you who are extremely confused by this, I suggest that you go on Google and you look up hyperbolic cotangent or hyperbolic trig identities, and then you'll see a bunch of these identities, and one of them is going to allow you to do this thing that I did here, where I rewrote this expression into this expression. Okay, there's a very simple identity which I'm not going to prove here, and I'm just going to use it. So if you look at this, this is equal to this, so they cancel, and we're just left with n delta mu hyperbolic tangent of b over 2. Now, this is of course it is equal to the result that we have got from before. And I believe that is all for part F. We have successfully reduced our current expression back to an old result just by plugging in j equals 1/2 and using a trig identity. I'm not even sure if it's called a trig identity or a hyperbolic trig identity, but whatever. It's just a math result that we used, and we got our desired expression. That's all for this problem. Thank you very much. See you in the next video. Bye.